Okay, don't do that to me. So the door's closed. Send me an email if you have a question. So current is in amps, and that would be current density times area. That's the current that's going through this area, right? We've got current going in this way because electrons are coming out, but we've got current going in this way through this area of square centimeters. That's where there would be a current flowing, because due to this charge that we've set up, we have some voltage there, and voltage per distance makes so voltage per distance makes an E field, and that's going to cause current or drift velocity, and that velocity is, if we know the number of electrons per cubic centimeter or the number of holes per cubic centimeter, multiply that by the charge on one electron or one hole, we'll get a current density, and multiply that by area to get a current. And we can find a whole current density. The same way. Now we'll have Q times P times the drift velocity. And again, that's going to be coulombs times the number of holes per cubic centimeter times centimeters per second. And that will give us a current. And the same way, I sub n or I sub p would be J sub p times the area that it's flowing through. Now, we don't actually know velocity, right? We usually don't know this number of velocity. We could calculate it, but we don't actually usually know that. But we know mobility, and so we know mobility is connecting us to velocity and electric field. Electric field is volts per distance. So we can actually say that we've got J sub n is equal to minus Q times n times the drift velocity. And the drift velocity, we know what it is due to the mobility, is Q times n times E times the electron mobility. And the whole mobility, in the same way, is Q times P times the drift velocity of holes, and that's connected to mobility. So that's Q times P times E times mu sub P. Now, these don't have to be equal to each other. The electron hole concentration might not be the same. I guess I should mention, so here we've got units of coulombs times n, which is number of electrons per cubic centimeter, n times volts per centimeter, and times centimeters squared per volt second. And if we multiply these all through, we've got centimeters squared. That's going to take care of that. We've got now centimeter times centimeter, so we've got per centimeter squared. We've got coulombs. We've got volts canceling off there. So we have coulombs per second times 1 over centimeter squared. So we get the same current density and the units work out again. So if E is going from plus to minus, then current is going the same way, whether it's J or I, and holes are going that way, and electrons are going the opposite way. Current flows in the direction of the holes in the field and the opposite direction of the electrons. Now, both electrons and holes contribute to the total current. Oops, JE, what am I saying there? both electrons and holes contribute. Let me write that the other way. I don't think it matters. So we can write this out. So that equals Q times N times E times the mobility of N plus Q times P times the field times the mobility of holes. And if I rearrange that, then I've got N times the mobility of electrons plus P times mobility of holes times Q times E. And this much is usually a constant. The field will vary as we change voltage on it, but usually that N times mobility, the electron concentration times the electron mobility plus P times the hole concentration times the hole mobility, add those up and multiply by Q. That's usually a constant, and we call that constant conductivity. So sigma equals conductivity, and it's in kind of odd units of 1 per ohm centimeter. So that makes no sense to me. It's hard to know exactly what a 1 per ohm centimeter is, but we often actually characterize it with resistivity. Which is 1 over conductivity, and that equals units of ohm centimeter. I still can't tell you what an ohm centimeter is, but it's just the units that we use, and we can certainly make comparisons of what ohm centimeters would mean for different materials. So so J is equal to sigma times E, because this is all this constant sigma, which is equal to E over rho, the electric field over the resistivity. And basically this is like Ohm's law, like I equals V over R, right? We've got a current. This is current density here. We've got current. We have volts per centimeter, or we have volts, and we have ohm centimeters. Here we have ohms. So if you kind of ignore these extra centimeters tossed in, we have something that looks very much like Ohm's law. V equals IR, E equals J rho, or J sigma, or E sigma equals J. It's very, very much the same. Now, that's one way we can get a charge to move, is by applying a voltage to this this chunk of semiconductor. If we apply a voltage, then charge will move, and we'll have a current. Another way we can get a current to flow, though, is if we just have charges that are separated. If we have a whole bunch of electrons on one side, that'll make a voltage, actually, and that would make charge 1 a flow. They're connected. I'll get to that. If we have a whole bunch of carriers, I don't know what these are. They're either electrons or holes, carriers. Let's see, we got many. And over here, we've got few carriers. What nature wants is, so here we have a gradient We have a carrier gradient. Nature wants uniform. Nature wants to spread these carriers out in this chunk of semiconductor. Maybe that's roughly speaking uniform. Nature wants it to be uniformly distributed. Nature wants to have all these carriers spread out. So if we have, for some reason, a whole bunch of carriers on one side of a semiconductor and a smaller number on the other side, then that's going to cause these carriers to flow. This heavy concentration is going to move in the direction of this low concentration until it achieves this situation of uniform concentration. That's what wants to happen. That's what nature wants to happen. And that means there'll be a current flowing due to diffusion. And we can write the diffusion current, Jp is equal to minus Q d sub P times the concentration gradient of holes. And similarly, we have, there's a minus sign there. It just depends on how you get the diffusion in the x coordinate system. Electron current due to diffusion would be Q times d sub n, the diffusion constant for electrons in this material, times d of n, or the concentration of electrons as a function of distance. And d, that diffusion constant, for holes is equal to about 35 centimeters squared per 35 centimeters squared per second, and it's about 12 centimeters squared per second for holes, for electrons, if I've got that right. No, that's just the opposite, I think. I think electrons are about 35. Now, actually, drift and diffusion current are connected. If we have a gradient of carriers like this, we've got a lot of electrons here and a few electrons here, or a lot of holes here and a few holes there, that means we'd have a voltage across this material. We'd have, for instance, if it's electrons, we'd have a negative voltage here compared to here. So we'd have a field across this distance. We have a concentration gradient, and we have a field, not a gradient, we just have a field across there, and that will make drift velocity, which will make drift current, and the concentration gradient will make drift velocity, and these two are connected by the Einstein relation, which is d of n over mu sub n is equal to d of p over mu sub p, which is equal to kt over q, which is equal to, in this class I'll use Vt, which we'll call the thermal voltage, and the units are in volts, right? It's about 25.8 millivolts at room temperature. 26 millivolts at room temperature, and this is the Einstein relation. It applies to more than just semiconductors. It applies to all kinds of situations, but it's important. It tells a whole bunch about what's going on, and it explains that connection between drift velocity and diffusion current, drift velocity leading to drift current, and diffusion current leading to or diffusion leading to, or concentration gradient, I should say, leading to diffusion current.